Part of what I'm going to do is a little change from the previous talks, although there will be some continuity. I'm not going to talk about climate policy. I'm not going to talk about climate negotiations. I'm going to talk about the impacts of climate change, but I will maintain continuity by continuing to be pessimistic. So why is it important to pay attention to estimating the damages? And I would say it's essential for macro-scale policy, setting a tax, setting a cap on emissions, and it's also being used in the US for micro-scale, evaluating particular mitigation policies. The discussion earlier today characterized the problem as one of free riding, and it may be that. I see it as one of weakness of will or procrastination. St. Augustine famously prayed to God to make him chaste, but not just yet. And I think in developing countries, that's essential, in developed countries, that's the philosophy towards dealing with climate change. And I think in the US, or one of the differences between the US and Europe is the perception, long-rooted in the US, that the US has relatively little to gain because it faces relatively little damage from climate change. Other countries, small islands in the Pacific, face risks, but small islands in the Pacific don't get to vote for Congress, and we are pretty well protected. The damages I'm going to talk about are part of integrated assessment models. Christian gave an explanation of integrated assessment models. In principle, they track from economic activity to the generation of emissions to changes in the atmosphere to warming and then to impacts. So actually, there are two types of models. The majority just trace from economic activity to emissions to radiative forcing to changes in temperature and stop there. And those models are used, for example, to examine mitigation policy to meet a climate target. There's only a handful of models which then translate the warming into impacts on people and damages, and through what's called a damage function. And that's what I'm talking about. The three main models date back to the 1990s. There's a model that the World Bank developed about 5-6 years ago. But the three best-known models, and there's some variants. Carlo-Carraro's group has developed a model. So in total, there may be 4 or 5 models. The three best-known, the three most used in the US are these. And while they've evolved, they've been updated, in my view, to capture latest information from the IPCC on the carbon cycle. The damage function representation hasn't undergone major changes really throughout the last 2 decades. I'm arguing, I believe that they are now at a crossroads for various reasons. They received withering criticism from Bob Pindyck a couple of years ago. The federal government has used them to develop estimates of the social cost of carbon, which are being applied to new regulations, and there's been a pushback, and there was actually a trial on that subject in Minnesota a month ago in which I participated. And there have been important developments, first in the conceptual literature, including work by Marty Weitzman, work by Christian Gollier, work by Christian Traeger, and also growing work, empirical work. So let me start with Pindyck's views, which argued that there's no theoretical basis for the damage functions. In my view, that's a bad criticism because I don't see why economic theory would have anything of great substance to say about how people are hurt by wildfire or electricity or so on. But Pindyck's other criticism is that they're made up. The numbers, the formulas are made up. So let me start. So let me say, he's right to a degree, and he's wrong to a degree, and the situation is a little more complicated. So the first thing is, damages are represented as a fraction of the output that would be produced if there were no warming, and warming is the only variable that's tracked, and obviously it's a major one, but effects on precipitation or humidity or other things are not modeled because it's too hard to model those in a simplified manner in these models. And I want to talk about the calibration. My remarks apply particularly to two of the models. But it's important to emphasize the formulation that the impact in a given time period is proportional to the output that would otherwise have been produced, and the proportion just depends on the current warming, implies that the impacts are reversible. That is, if you reduce emissions and you have less warming, then you have less impacts. And this, I think, is fundamentally false in many cases. The parameters are essentially, there are two parameters. The D is the percent of GDP that's lost as a result of warming. Delta T is the amount of warming. There are three parameters, A, B, and delta T star. Delta T star is a benchmark warming, and it's typically the amount of warming assumed to occur with a doubling of CO2, the amount of warming that will occur ultimately when a new equilibrium is restored, and that's typically about 2.5 degrees Celsius, in some cases a bit more, sometimes a bit less. And so the assumption is with no warming, there's no damage. When the warming equals the benchmark, the damage is A, and then the parameter B just tells you how much more or less damage there is when there's more or less warming than the benchmark. A is based on estimates, mainly from the literature in the 1990s, of the impact of a doubling of CO2. B is a guess. In DICE, it's set at 2. In PAGE, it's random and can take the values 1, 2, 3. FUND has something more complex. As I say, estimates of the damage associated with the doubling of warming come from studies done in the 90s. We have now 0.8 of a degree of warming, so, but none of the damages right now are based on the current warming. So let me just say, if you look at the three models I described, between them they cite maybe 50 papers, almost all of them now 14 or 15 years out of date, or old. The literature has really exploded in the last 15 years. And these are some statistics on the increase in the number of papers in the last 15 years. And the point is there is a very large growing literature. And the newer studies in general have more spatial detail and reach more pessimistic conclusions and are not reflected in the three models. These are the damage functions. Green is FUN, which shows warming, benefits of warming up to just under 3 degrees. Blue is PAGE, red is DICE. I'll come back to that. So the question really is, should one believe these damage functions? One question you could ask is, do they line up with estimates of the warming we're experiencing now? Are we, for example, experiencing net benefits overall, as FUND suggests? That hasn't been addressed, that question, and I think it should be. Another thing you could ask is, what's the sectoral decomposition of damages? And the short answer is that differs in strange ways among the three models. This is a summary for two of the models. And to put it simply, the models disagree. I could add a third model to this on the breakdown and reach contradictory conclusions on the impacts in individual sectors. And so this raises the question of why the aggregate number should be believed if the sectoral breakdowns seem odd and implausible. Quickly, I want to talk about the federal government's use of the social cost of carbon. It was done in 2010. It was repeated in 2013. It's been used for maybe 30 regulatory assessments by the federal government. As I'll mention, Minnesota has proposed using it when regulating investment plans of utilities in Minnesota, and that has led to a trial. I'm going to give you a little more detail, but the central number recommended by the federal government is the 3% value, which would be $36 a ton right now. The federal government used the three models, weighted them equally, standardized the emissions, switched DICE from an optimal control to, the federal government took external projections of GDP and emissions and fed them to DICE as well as to the other models. They also added, I'll come back to the emissions, they did a Monte Carlo sensitivity analysis using the Rowe-Baker distribution, 10,000 draws from the Rowe-Baker distribution, 3 discount rates, 5 emissions scenarios, 150,000 simulations for each model. They first of all ran each model with a particular climate sensitivity and a particular emissions scenario out to 2300. They then went back and shocked emissions in a particular year, 2010 or 2050 or whatever, reran the model with the shock in just that one year to 2300, calculated the difference in warming each year and the difference in damages each year, and took the discounted present value of the extra damages using 2.5%, 3 or 5%. This is the probability distribution, the black line, and it ranges from 1.5 to a high value. The 90th percentile is 5.68. This is the probability distribution of 450,000 estimates of the social cost of carbon for each of the 3 discount rates, and that's across the 3 models that was used. The 3%, the average for the 3% discount rate is 42. That's essentially the number I showed you. This is a slightly older diagram. Let me talk quickly about some of the issues raised in that proceeding. But the first thing to say is this is the first time there's been a model intercomparison of the IAMs. Up to now, basically, DICE is readily accessible. Fund is in principle accessible, but you're warned on the web page to change the model at your own peril. And with Page, you pay Chris Hope to run the model. Nobody until now has been able or has succeeded in running the 3 models side by side. It's known they're different, but in a sense, there's much more insight because for the first time they were run side by side. More importantly, the electricity industry, which was clearly concerned about this, paid to recode all 3 models in the same code, which is now being done by EPRI. And that would open the way to mixing and matching model components, although that hasn't been done. One of the issues was in order to make them comparable, the optimal control feature, which is in DICE but not in Page and Fund, was switched off, and that was criticized. So I'm a microeconomist, not a macroeconomist, and I'm an environmental economist, not a real economist. And so I have less innate loyalty to optimal growth models. The notion that you run a model as though a single long-lived, infinitely lived person controlled the world's capital investment strikes me as not entirely plausible. I therefore doubt whether the optimal control model in DICE has any predictive validity in predicting future investment. So my own view is that it actually probably helps to take external projections of income and emissions and not generate them from an optimal control. The federal government used 4 BAU projections, I'll show you in a minute, and then a 5th one which corresponds to RCP 2.6, something like that. Industry criticized these emissions. Industry said that the federal government was too pessimistic about what future emissions would be. These are the 5 emissions scenarios used by the federal government. Maybe, let me show you one. Let me show you actually a couple of things. So this is interesting. This compares from around running DICE. the way Nordhaus runs it in an optimization mode, and then running dice with one or a mix of the BAU scenarios. The social cost of carbon is more or less the same. But if you look at the emissions, you get a peak warming of over 3 degrees. Under the optimal model, you get almost 7 degrees warming. With the reversible damage functions, under the optimization, this single infinitely lived person figures out that in 2130 he'd better start reducing emissions. He does reduce emissions. The warming goes back down from 3-point-something Celsius to a third. It goes down by 90% by 2300. In a business as usual, that big reduction doesn't occur. The only reason the social cost of carbon isn't much lower is because the high temperatures and damages occur by 2200 and by 2300, and with discounting, that doesn't show up very much. This is a diagram from the fifth assessment report of various emissions projections. The black line is the emissions right now. Most recent data is for 2014. Through 2014, we've been on the BAU, the RCP 8.5 scenario. That's not to say we won't, get below it in future. But all I'm saying is right now, if you look at the emissions, you don't see any change. After Paris, 5 years from now, you might, but it's grounds for not optimism. I want to show you the effect of different time periods. So one tends, at least I've tended to look at 2100, and it was eye-opening to see the results through 2300. So 2300 is a long way from now, but in a sense, in terms of the history of mankind, it's worth considering. So if you use the median climate sensitivity, so you see the blue line is the low emissions that it's key to a 2-degree warming in 2100, and that's what happens. And by 2300, there's a bit more warming, but not a lot. The other three give you warming of between 5 and 8 degrees in 2300. This is if you have the 90th percentile of the climate sensitivity, which is way out in the tail, but you see you get a lot of warming by 2300. In 2100, you're maybe 5 degrees warming, but by 2300, this is really very toasty. That summarizes this. So this is the point about discounting. If we are looking to $2,300, with a 3% discount rate, $100 counts as 1 penny, and with higher discount rates, it doesn't count at all. We've always known that discounting is a crucial issue. These diagrams brought that home to me. Saying let's look to 2300 instead of 2100 strikes me as not that incredibly wild, but there's a huge difference. There's a big scientific literature on tipping points, but probably the tipping points, if they occur, will occur in the time frame after 2100, and with discounting, maybe they really won't matter very much. And so in my own mind, there's the question of whether we should be doing more about discounting. And I list here several factors. The one that I find most implausible is the least discussed. The notion that mankind will have the same preferences over 300 years, that you won't get used to a given standard of living and raise your expectations. That's the model Ryder and Heel proposed, and that would greatly knock down the second term in the Ramsey factor, the increase in income leading to a big reduction in the marginal utility. And that itself would lower the discounting. What about the uncertainty? There were criticisms. The federal government used the mean, not the median, which would have been lower. It was suggested this was the electric utility. The red lines are the range of values. It suggested the interquartile range. So let me say this, the real issue is, should we be serious about the tail or should we ignore them? Come back to the damage function. The damage function suggests at 6 degrees warming, you lose between maybe 3% and 8% of GDP. Now, some scientists talk about 6 degrees warming as being a barrier we shouldn't pass. If you look at these damage functions, it sure doesn't look like that. I mean, the reduction in GDP and the Great Depression, or even the recent recession, would be sort of comparable to what you get from 6 degrees warming, and we've kind of survived that, and what's the big deal? Well, one thing is, you have to, so there's a distinction between a change in weather and a change in climate. There's a distinction between global climate and local climate. So these are some numbers. An increase of 4 degrees in global average climate corresponds to 5.8 degrees in average climate in California, and to essentially 10 degrees in the summertime in the major population and farming areas. And maybe 4 degrees sounds livable, but 10 degrees really has a different complexion. Moreover, the changes we're talking about, it's been warmer than today, maybe 3 or 4 times in the interglacials. It's been 2 degrees warmer than today, almost 3 million years ago, before Homo sapiens existed. It's been 6 degrees warmer than now, about 40 million years ago. And so these are changes on an amazing time scale. The last topic very quickly is the recent work on estimating damage functions and focusing on pathways by which impacts might occur: labor, loss of capital, human capital, impact on people's productivity. There's the macroeconomic, the work by Dell et al., which received a lot of attention, which found an effect of warmer temperatures on growth in GDP in poor countries, but not in rich countries. But then last week, Nature published a paper, Thomas gave a very nice commentary on it, which extended the data by 7 years and found an effect on growth in developed countries as well as developing countries. And the effect on developed countries' growth is smaller, but it's still there. This is, you see here, the damage functions for fun, pain, or dice are kind of shown at the top, and on this scale, they differ greatly from what you find from this econometric. This is looking at variation in annual temperature across whatever it is, 100+ countries, how it affects annual GDP, and that's very different. So there are a number of issues. GDP is not a welfare measure. What we're talking about is a change in climate, not a change in weather. That can be different. It could be smaller if you think of the Le Chatelier principle and adaptation. But there are also things that can be done in the short run, not in the long run. So California had a drought. There was a massive overdraft of groundwater. You can do that 1 year. You can do that 2 years. You can't do that permanently. And so it's not clear that we're reflecting things. Very quickly, I want to argue that the studies, my own work and some other work, suggest most of the impact, if you look, this is at agriculture, most of the impact of agriculture on farmland value is associated with extreme warming, not warming in the normal range for growing crops. And for the next 3 or 4 decades, that accounts for maybe 90% of the impact. And even at the end of the century, when there's been more overall warming, it will still account for maybe 60% of the impact. This is from another recent paper by Sol Shang, and this shows the effect on income per capita in US states over 50 years of daily weather in different ranges. And you see essentially all the effect is associated with daily weather over about 65 or 68 degrees. Almost all the real impacts, but essentially it's the increase in temperatures over whatever, about 70 degrees that count. This is data on heat waves which occurred 10% of the time before 1990, occurring essentially all summer in the case of LA. High emissions. And so this is different from Marta's emphasis on sort of catastrophic events and large changes. These are changes what I just described. More hot days, more 80 or 90 degree days than 70 degree days. These are not catastrophic, these are not global events, but they make a big difference to the well-being of the particular people in that area who experience them. And these are typically not reflected in damage functions because the damage functions look at average annual temperature, and these are a few weeks of hot days, which will barely show up in the average temperature. There's been an important development in the literature, which I'm going to skip, on conceptual issues. The bottom line, I think, is the existing damage functions, which we've become used to using in DICE and elsewhere, I think are likely way too low. And this is really my last point. We face considerable ferment and doubt about our existing damage functions. And I think if one looks out 200 or 300 years, not just 100 years, these are major threats, and how we should think about them and how we should reflect them in carbon policy, in climate policy, and in climate pricing, I think is an open question. For me, what I hadn't realized before I started looking at this is really the changes we might experience over the next 100, 200, 300 years are unprecedented on a time scale of millions or tens of millions of years. Thank you.